Hello there, and welcome to the online materials of Machine Learning for Audio Signals in Python. This is a course offered by Professor Schuller at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about the neural network basics, and we'll start looking at neural networks as detectors. So let's get started. The simplest layer is the so-called fully connected layer. If we have a one-dimensional input array X with a certain length, let's say the length is given by n features, and a one-dimensional output array Y of a certain length, and this length is given by out features, then the function of this fully connected layer is simply a matrix multiplication with an addition of an array B, that's called bias, followed by a nonlinear function called the activation function. In PyTorch, the matrix multiplication and addition is implemented in this function here. So the linear layer computes the function y is equals to x multiplied by A transpose plus B, where T here is the transpose operator for the matrix. The coefficients of the matrix A and the array B, they are called weights. So, and they will be obtained, these weights will be obtained by using optimization. That's also called training in neural networks terminology. You can take a look at this function in PyTorch. Looking at the PyTorch documentation, we have here this linear, and it applies a linear transformation to the incoming data y equals x times A transpose plus B. And here we see the in features, the out features, and the bias. So this is the size of each input sample, the size of each output sample, and bias here it can be set to false if we don't want to use bias, or it can be set to true, which is the default. This is called fully connected because the matrix A connects each input element, so also called feature, to each output element or feature. The input and output arrays, they are one-dimensional because of the full and fixed connectivity. If we have an image as an input, we will just have to reshape into a one-dimensional array, for instance, using view or reshape in PyTorch. Often neural networks are used as detectors. In that case, each value in the output array Y would correspond to the output of one detector, and each detector represents one class. This linear layer is usually followed by a nonlinear function, also called an activation. For instance, the rectified linear unit function can be applied to each output element or feature. So this is also called the ReLU, the rectified linear unit function. This function applies the element-wise function given here. So this function limits the output to the non-negative range, and this is useful when the output represents a detector. In this case, a value of 1 might mean detected with certainty, and a value of 0 would mean not detected with certainty. Here, negative values would make no sense. This is probably the most often used activation function because of its simplicity. In PyTorch documentation, you can also take a look at the ReLU, and it applies this rectified linear unit function element-wise given here, and we have all the documentation about this function. Often, a slightly modified version is used, which avoids the vanishing gradient for negative values, which helps the optimization. In this modified version, it has a small slope for negative values, and it's called the leaky ReLU. And we can also take a look at the PyTorch documentation of the leaky ReLU, and we see that there is a small slope here, and we can set these values So we can, there's negative slope, is a float that by default is 0.01, but we can change this, and this leaky relu will apply this function here. So we have this negative slope times the minimum of 0 to x. Another activation function is the softmax, and the softmax activation function turns the outputs of a network into looking like a probability function, positive and summing up to 1. So this is another very used activation function, and again we find in the documentation it's given by this equation here. This is the softmax, and this applies the softmax function to an n-dimensional input tensor, rescaling them so that the elements of the n-dimensional output tensor will lie in the range of 0 to 1 and will sum to 1. An alternative activation functions is the so-called sigmoid function, which is differential everywhere, but it's more complex to compute. This is the classic activation function, which is already used in the early papers about neural networks. And the sigmoid is given by this function here, and we find it. You can also look, see how it looks like in PyTorch documentation. We will now take a look at the Python example for a linear layer. So for a linear layer, the shape of the input and the output tensors are given here. So we have an input, given the shape is n star h in, where star means any number of additional dimensions and h in means the in features like we've seen before. The output has the shape n star and h out, where all but the last dimensions are the same shape as the input, and h out is the out features like we've seen before. Capital N is a batch size. Star is usually the index for the test set. H in is the length of our input signal, and h out is the number of classes or detectors that we desire. The edge index is for different sets of training and data. Optimization is performed one batch after the other. This saves memory because only one batch is loaded in memory. In our example, let's imagine that we have two input signals that we want to detect, one increasing and one decreasing. So we have here x0 is given by 1 and 2, and x1 is given by 2 and 1. We will assemble these two signals into a two-dimensional tensor, a matrix, where each signal is one row. So now we have this matrix called x, and here we have the x0, 1 and 2, here we have x1, 2 and 1. We want to have two detectors, one for the first signal and one for the second signal. The desired output of the first detector should be 1 for the first signal x0 and 0 for the second x1. On the other hand, the second detector should output 0 for the first signal x0 and 1 for the second signal x1. The desired output is also called target in deep learning, machine learning, neural networks nomenclature. We assemble the desired outputs for targets in a matrix where each detector corresponds to one row. So here we have the first detector. Like we've said before, it should be 1 and 0 for the first signal, and 0 and 1 for the second x1 signal. For our linear layer, we now need to find the weights or the coefficients of the matrix A and bias B such that the desired output Y is approximated, given out the training set X. So we have that this matrix should be our input matrix X multiplied by A transpose plus B. This is a matrix of coefficients or weights. This is the bias. And in this simple case, we can actually find a closed form solution. So if bias is 0 and 0, and the A transpose is the inverted X times Y, then we have a closed form solution for this problem. If now we have more samples in our training set for X and Y, we will get tall matrices. For instance, we could add another input x2, for example, 1 and 1. For each, both outputs should be 0 as target. For the non-quadratic matrices, we can compute the pseudo-inverse, which minimizes the mean square error between the network output and the desired output. And it's given here in these equations. Observe that this does not include the bias array B, which might lead to better approximation and also needs the mean squared error. Depending on the application, we might want to use a different error measure, also called loss function. A simple and widely used loss function is the mentioned mean squared error loss. So PyTorch has this function implemented, is mean squared error loss, and for detectors of different classes, usually the so-called cross entropy loss is used. And it creates a distance or divergence function between two probability distributions. Here, the probability distributions are the target distribution, probability 1 for the true class and probability 0 for the false class, and the distribution that the neural network generates, a predicted probability for each class with high probability value for the class that the network thinks is at its input. In PyTorch, we have also this cross entropy loss, and you also find all the details in PyTorch documentation. To obtain a better solution, include other loss function. In general, numerical optimization is used to find the weights of coefficients which minimizes a given loss function. Observe that the loss function produces a single number or value for a given training set and given weights. The weights are then updated during the optimization to reduce the loss function. Common optimizers are, for example, the stochastic gradient descent, SGD, and adaptive moments, ADAM. After we obtain the weights from the optimization, we have to see if it generalizes to other examples or just works on the training set. For this, we have the validation set containing new input and target samples. This is used to modify the neural network structure until it performs on new samples or examples sufficiently. Once we have a good neural network structure, we test it on the test set, another set with new samples or examples to test the performance. We start our program with importing the PyTorch library, and then we select the device we are going to use. So if you have a GPU on your computer, or if you're using, for example, Google Colab, you can set the device to CUDA, or if you're using a normal computer without a GPU, you can set it to CPU. Then we define out our neural network with a linear layer and a nonlinear activation function, which we can comment out on the forward function if we want to test the network without the activation function. This is done as a class such that the network is an object which we can instantiate and initialize in the main part of the program. This is our first experiment, and here we are defining the class. So this is how we can, one of the ways we can build a model in PyTorch. Here we're using linear layer, so in features is equals to 2, out features is equals to 2, and we're using bias, so we are setting bias to true. Here in the forward section we see that the output just goes through this layer, and we are commenting out here, so we don't have an activation function in this first experiment. And here we can see that we comment, if we remove the comment, we can use the leaky relu or we can use the relu as activation functions. But for this first experiment, we are going to look just at what the linear layer is doing. So here we define our class, and in the main part of our program, we will generate the data for training and for validation. So here we are defining our training set. So we have 3 vectors, and there we use a PyTorch tensor. And this is how we have our data in PyTorch. They use tensors, and tensors need a special shape depending on the layers and depending on the input. And so you need to pay attention on how to set up the inputs and outputs and the layers and models in PyTorch. So here we are adding the first dimension for the batch. So we have our tensor, and we can see the shape now is 1 by 3 by 2. So we have 3 features, each 3 samples, and each sample has 2 features. So 1, 2, 2, 1, 1, 1, x0, x1, x2, and this is how we're doing an input for our training set. And our target, as we mentioned before, so we have 1, 0, 0, 1, and 0, 0, and we also prepare and reshaping, and we have that the input and the target now they have the same shape. Here we have batch, sample, and features, or the signal dimension. So here's 1 batch, 3 samples, and the signal dimension is 2. Observe that the validation input data contains a scaled version of the training set. Now we instantiate the model, define the loss function and the optimizer. So here is what we are doing. Our model we are instantiating. So this was our linet in here. So linet. Here we defining our loss. So we are using the mean squared error loss function from PyTorch. So here we are defining our optimizer. We're going to use the stochastic gradient descent. And we will start with the learning rate of 0.1. So we have here our loss, and our optimizer has a parameter is learning rate 0.1. Here we also have 2 choices of optimizers. So here you can see that this add-on optimizer is comment out. So we can replace, we can try which one works better. Next, we let the optimizer do 10,000 update iterations. They are called epochs. So this is what we're doing for epoch in range of 10,000. So the Y predictions is the model of X, so the model produces prediction output. Here the prediction and target are compared by loss. So for every 100 we are printing the epoch and the current loss value. So we see that we start with a high loss, and our loss is decreasing until it's a very small value, and we see that there are no further decrease after a certain point. Here is typical for PyTorch experiments. We use this optimizer 0 grad, that the optimizer sets previous gradients to 0. Loss backward is the optimizer computes new gradients, and optimizer step, so the optimizer updates weights. Oh, this is very typical in a PyTorch experiment. We always have, so we have the forward that we defined in the model. We have here the 0 grad, we have the loss backward, and we have optimizer step. And here we ran our experiment, So finally, we'll print out the results on the training set and the validation set and the obtained weights. And we see here we have the loss in training was here, very small loss, but we see that the loss on validation set 0.5. So we see that we didn't do a very good job because it works really well on training, but it doesn't generalize well. So on the validation set, it's just a very high loss. So each time we execute it, it starts with a different random initialization. Hence, each time we get a different route that the optimization takes, and possibly different results of the optimization. If we get very different results, then it's a sign that optimization got stuck in a local minimum, for example. Observe that we obtain the desired output on the training set, but the output for the validation set doesn't look good. This is reflected by the loss values, as I mentioned before. We have very small value to the order of magnitude of e to the power of minus 12 on the training set, but 0.5 on the validation set, and this is a very big loss. So it demonstrates that we have a bad generalization. In our experiment number 2, we are going to modify our neural network structure, trying to obtain a better generalization. And we will do that by adding the activation function. So if we look at the code, we are uncommenting the leaky ReLU, and we are also uncommenting here so our output now is first goes to the first layer, which is the linear layer, and then we apply an activation function, which is the leaky ReLU. We will not make changes here, so we are still using the stochastic gradient descent optimizer. And here also we are not changing anything. We just run our model and we see that we have different results. So now the loss for our training set is 1.8 in the magnitude order of magnitude 10 to the power of minus 5, but we have the validation loss is 0.144. When we compare the previous experiment, it was 0.5. So we already have some good reduction on the validation set, meaning that our model is generalizing better. So here we get a loss. Our training set is a very small value. For the validation set, we get 0.441, so it's much better than before. So using this activation function helped for better generalization. In our final experiment, we are going to change the activation function. We are going to use the ReLU, and we will see the effect of vanishing gradients on the optimization. So this function has a constant 0 for negative values and hence a vanishing gradient for negative values. So what we do is now we are not going to use the leaky ReLU, we are going to use the ReLU. And here we didn't change in our forward part. We're still using the same optimizer, no changes here. And we see that we run our experiment, but we see that the loss gets stuck and is not changing after some time. And here we see that even in the training set, the loss is 0.166. So the optimizer gets stuck at a loss value of 0.166 to retrain, and this is caused by the vanishing gradient of the ReLU function in the negative input range. So with these 3 experiments, we've seen the effects when we are not using activation functions, when we are using an activation function, and we need to be aware of the characteristics of our data, the characteristics of our network architecture, and the characteristics of our optimizers. So there are thousands of parameters we can change, and we need to have a certain intuition on how to fine-tune our model to achieve the results we want. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals. This is a course offered by Professor Shula at the Ilmenau University of Technology. I am Renato, the instructor for these tutorials, and on this notebook we will talk about neural network as function approximator and regression. So let's get started. We can use a neural network to approximate a function. For example, y equals to a function of x. In our simple example, x is a sample, a one-dimensional sample, and y is the target, also a one-dimensional, also called regression. This function could be, for instance, an audio signal, like a tone, which could be a sinusoidal function, for example. Here, x would be the time dimension, and y would be a sample from or to the sound card. In PyTorch, we have a torch.syn function, which directly produces a torch tensor, and also a torch rand_n function, which produces random numbers according to a Gaussian distribution with zero mean and unit variance. We can use this to simulate a microphone and pick up noise, for example. So we generate our target function like this. So here we are setting the number of samples in our signal. For our input, we're generating n time steps for x. This is what we're doing here. Then we are reshaping to have the last dimensional for the signal and the first dimensional for the batch size n, capital N, that we're defining here. Then we are using this torch.syn, and we are generating two periods of a sinusoid that will be used for training, and we are adding some noise. So here we have x, so it's this array of elements, and this is pi, and then so here we are generating two periods of the sinusoid, and then we're adding some noise using this rand_n function. So often we want our network to interpolate the function between the training samples and also to extrapolate beyond the training samples. Hence, we construct a validation set which has the x samples between the integer values of the training set and extend it to beyond the length of the training set. We can see how robust our network is against the noise in the training set. We also add some noise. So for a validation set, the test to test the generalization with new noise, so this is what we're doing. We're generating now 2 times capital N time steps for x for extrapolating beyond n. So we have a signal that is 2 times longer than what we are going to train our network with. And also we are reshaping again, and pay attention that now this is shifted by 0.5 compared to the training set for interpolation between the original sample points. So we are reshaping here, and now we have our validation target. Again, we are using torch_syn and adding some noise, but now we see that we are having twice as long as our training input here. So this will be x, and this will be xval for validation and y validation. So now we have to decide what kind of network to use. We will try to find one which is as simple as possible for this task. So we choose a structure which is in principle able to approximate the function piecewise. So we will use a number of nodes in this network, and each node is in effect responsible for a piece of the function. We can do this with, for example, a 3-layer fully connected network with an activation. And you can also take a look at this tutorial explaining a multi-layer neural network and also the neural network model. So this is some reference of what we are doing. In our example, the first layer is the input layer, which takes one input sample of X and then distributes this sample to capital N hidden nodes with weights, and each node then has a bias which basically activates for a certain value range of capital X, and the activation function, for instance the sigmoid function, which is mainly active in the input range of -4 to 4, followed by weights to the output layer, which in our case is simply one node which sums up all the inputs from the hidden nodes with weights but no activation function. We can see the structure of this network in this picture here. So we have our input sample, we'll have our input layer that will take this input sample and then we'll distribute to n hidden nodes with weights, and each node will have a bias and activation function, and then they will be followed by the output layer that in our case just will add all the inputs from the hidden nodes with weights but without any activation function. We can see the structure of this network in this picture here. So we have our input sample, we'll have our input layer that will take this input sample and then we'll distribute to n hidden nodes with weights, and each node will have a bias and activation function, and then they will be followed by the output layer that in our case just will add all the inputs from the hidden nodes with weights but without any activation function. So we will define our 3-layer neural network with the following class in PyTorch. So we are defining the number of nodes that we want to use. So we are using 10 nodes. Then it will be a 2-layer fully connected layer with one input time value, and then hidden layers that has capital N nodes and one output function value. So this is what we're doing. We're defining this class called LinNet, and then we're having here first layer, and it will be linear layer. We have features equals to 1, output input features equals 1, output features equals the number of nodes, and we are setting bias equals true. You're defining another layer, layer 2, that has the input features is the number of nodes that we defined earlier, and the output features is both equals to 1. Here we are defining our activation function. We are going to use the sigmoid. At the forward method, we are putting the network together. So here we are taking the output from the first layer, layer 1. Then there is the activation function acting after the first layer, and we get this second layer, and then we are returning the output of the second layer. So we see that there is no activation function in the output. So after we define the architecture of our network, we will first generate the training and validation set, then we will instantiate and initialize the model, and the model will be initialized with a random weight values. So here we are creating our training set, and like we explained before, so we have our input generates n time steps for X, and then we are reshaping, so we have the last dimension for our signal and the first dimension for the batch. Then we are creating the target, that here is a noisy function value, so it's sine function plus normally distributed random values, and this is what we are doing here. And we are also reshaping our target. This is our training set. For our validation set to test generalization with new noise, and we are also generating for extrapolation, we are generating 2 times capital N time steps for X, and this is what we are doing here for our validation set input, so X validation, and the validation target is Y validation. Here we are creating our network object and we are calling it model. So before training, we can take a look at the weights. So these are the weights in the initialization of the model. So it's before training. And then we can take a look at also the prediction before training. At this point, we will define the loss function and define the optimizer we are going to use. So we are going to use the mean squared error loss, and this is what we're doing here. And we are going to use the Adam optimizer. And here is where training in fact takes place. So this is where the optimization occurs, and we are using 10,000 epochs for our training. Here the model produces the prediction output. At this point, the prediction and the target are compared by the loss. We are printing the current loss value for every 1000 epochs. Here we are calling the zero grad, so the optimizer set previous gradients to 0. Here we use it so that the optimizer will compute new gradients and the optimizer to update the weights. So this is where the training takes part. After that, we can compute the resulting loss value on the training set and the validation set, and we can plot the obtained learn function in comparison to the noisy target function for training and for validation. So we see that for plotting we need NumPy arrays, so we will have to convert from PyTorch tensors to NumPy arrays, and we can use this NumPy here to do this conversion. And here we are now making the predictions based on the obtained weights. Here we are calculating the loss, so we can print, and we will plot the predictions. We will plot the target, so we will compare the training target with the prediction output, and it will be in our plot called results. And we will do this for the training and for the validation and see what happens. So this is the basic structure what we are going to use, and here is our code. So we are importing PyTorch, we are importing matplotlib pyplot for plotting. So we're defining n equals to 40, so this will be the number of samples in our signal, and we are going to use 10 nodes in the hidden layer. Here again I'm just showing how we define the structure of the architecture of our network, and we define and initialize the layers. We define the forward method, so we are putting the network together. Here we are creating the inputs and targets like we explained before. Here we create the network object. We see how things look before training, then we train, then we see how things look after training. So when we run these cells, we see the number of input samples is 40, number of nodes is 10. We see the shapes of our tensors. Here we see the initial weights. So this is the before training, so the weights here are initialized randomly. Then we start optimizing, and we are printing for every 1000 epoch, and this is the final loss on the training set and the final loss on the validation set. So we see that part of the printouts are the initial weights before the optimization that we see here. They are randomly initialized and they are obtained with these lines here, and it shows a dictionary of weights and biases. So this is what we see, the weights, and we see some biases. So observe the data format. The first dictionary entry is a layer 1.0.weight, which is a two-dimensional tensor or matrix, and this represents the matrix A of the first linear layer of our network. So you can take a look at the documentation of PyTorch for linear layers and take a look on how it works. Remember that the equation was given by here. So y is the output, x the input. We have this matrix transposed A plus B. In our case, x consists of just one feature. It's a one-dimensional, and we have n output features or nodes. So you can compare with the network picture in the first part. And A, this matrix A must have one column of n entries, which is what we observe. After that, we see layer 1 bias, which is the bias vector with n entries, or one bias entry for each output node. And then the layer 2 weight, which are the weights for the next layer, which has capital N input features and one output features. So this is the approximated function value. Hence, it has one row with capital N elements. And finally, we have the bias for this layer, and it has only one entry since it only contains one node. So that's what we see here. We have the weights for the first layer, the bias for the first layer, the weights for the second layer, and the bias for the second layer. Then the optimization runs and we obtain the losses. So this is what we had after we ran our program here. We got these outputs here, the losses for every 1000 epochs. So the loss on the validation set is somewhat higher than from the training, but less than a factor of 2, which is not too bad. If we increase the number of nodes to 80 or 100, we will observe that the loss on the training set will go down, but the loss on the validation set maybe go up, and this is a sign of overfitting. Also, we can try with different activation functions, like the leaky ReLU, for the case of, for example, 80 nodes, and it leads to a similar loss. And then you can try the ReLU, and you'll find that the optimizer has a much harder time to find a good solution because of the vanishing gradients of the ReLU activation function for negative inputs. So now we see the function plot for the 10 node training set, and this is what we have here. So we see our training target, which is in blue here, and it is a sine plus noise, and then we see our prediction output. We see that we get indeed a smooth version of the training set, which means our network is somewhat robust against noise on the training set. For the validation set, we have now, again, in blue is the validation target, which is now is 2 cycles of a sine wave with noise, and we have the prediction output, but we see that we have a good interpolation on the capital X range of the training set, but the extrapolation beyond this training set is not working. So we see that we start getting a sine wave, but at this point it just goes completely different. So the resulting function from the network is the sum of the functions of all the nodes. And to see the functions of the individual nodes, we can just keep their weight unchanged and set the others to 0 and plot the resulting function. And for that, we can mask with zeros for the weights of layer 2, except for one node, and then plot the function. So we can repeat this for every node in a for loop, and this way we can see the individual the functions of the individual nodes. And this is what we are doing at this part here in these 4 nodes. So for each node we are doing this weight mask, so we mask with all zeros for the output layer except 1. We leave one node unchanged, and then we see and we will plot. So these are the basis functions of the network. So we have for node 0, for node 1, for node 2, and so on. So each node has its individual contribution. Here we see that the activation function of each node is fit with bias and weight to different parts of the target function, since the activation function is only fitted over the training range. They all become flat after that, and hence their sum also becomes constant. And this is what we're observing here. So they all become flat, and then their sum will become constant. We will now change our strategy and change our network architecture. So instead of using fewer layers and more nodes, we will use fewer nodes and more layers. So we'll do what is something like a deep function approximator. So instead of having a relatively flat network with only 3 layers, we can now distribute our nodes over more layers, each containing fewer nodes. In this way, we obtain a more narrow and deeper network. So in this example, we can use 5 or 4 layers, but each layer will only have 2 nodes. So our PyTorch implementation is basically the same. We're just defining more layers and changing. So we are using 2 nodes, and then we have 4 layers, and the output layer, again, we have the activation function after each layer, but we don't have any activation function after the last layer. And we will do the same. It's the same input and target for the training set, and the same input and target for the validation set. We will use the same loss function and the same optimizer. We will just increase now the number of epochs, and we'll run our model, and here we see that it turns out that the Adam optimizer now needs more interactions instead of just the 10,000, so we needed 15 times more, but the resulting function approximation seems to be more smooth. So this is an advantage for the generalization, and we observe that the validation set now has a very similar loss when compared to the training set. Here we have our plot, and we have in blue our target, so it's a sine wave with the noise. Then the prediction, so we see it is smooth, and it's robust for against noise, and the optimization has a harder time to fit the function despite the 15 times more iterations, but often it is found that deep networks are better for generalization, which should give the loss for the validation and test similar values as for training. Here we are now plotting the validation set, so we have the extrapolation of not only 1 cycle but 2 cycles of the sine wave, and we see that we have reasonable interpolation, but again doesn't do a good job on extrapolation. And again we see the basis function of our networks. So those were 2 different ways, and we tried to approximate a function. We took care of interpolation, and we saw that it's not a this architecture doesn't show a good results for extrapolation, so we need to think about some different approaches on how to do this extrapolation. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about neural networks for classification. So let's get started. We saw in neural networks for detection that they need to detect if a pattern is present or not. For the classification tasks, we have a class of patterns, and we know that a pattern of one of the classes has to be present. The network has to decide which class. A classical application is the classification of handwritten digits. The network input are images of handwritten digits, and each image belongs to one of the 10-digit classes, from 0 to 9. The network usually has as many outputs as classes, 10 in the digit example, and each output might represent the probability that the image at the network's input belongs to the corresponding class. Since we know that it must be one of the 10 digits, the probabilities must add up to 1. A classical database for this example is the MNIST database, the Modified National Institute of Standards and Technology database. And you can read about this database here on this Wikipedia page. This database contains 60,000 grayscale images of handwritten images of size 28 by 28 pixels. PyTorch has a function to directly access and download these images in the Torch Vision dataset MNIST. So we will have now an example using PyTorch and using the MNIST dataset to use the neural networks as a classifier. So we will handle this problem of classification of handwritten digits. Let's start building up our PyTorch example. So we are going to use a data loader from the Torch utils data to load the training set with 100 random images and target classes, and we will test with 10 random images and target classes. After loading and then reading the training set with the next function, we can check the resulting data type with a print statement and with the type function. So this is what we're doing here. We'll just print and check the type of the resulting data. So we observe that we have a torch float tensor for the X-train type and a torch long tensor for the Y-train type. And X is our input and Y is our target. So observe that the input signals, the images, have the type torch float tensor, whereas the target, the correct digit class indices, have the type torch long tensor. So this difference in types becomes important when we apply a loss function. Next, we also have another print line to check for the shape and content of our data tensors. So we see that we have for the train shape, it's 100 by 1 by 28 by 28, and we have our Y-train shape is size of 100. So in the train data, we have the first index is for the image, so we have 100 image. The second index is for the batch, that only contains one batch, and the two remaining index are for the pixels. So we have 28 by 28 pixels, 28 vertically and 28 horizontally. On the Y train, we shows that we have for a target is a one-dimensional array of 100 entries. It is one number, the correct digit for each image. This can also be seen in the final part when we print. So we're printing our Y train and it's numbers with digits from 0 to 9. So for each image 20 by 8 pixels image, then we have a target which is the correct digit that this image represents. Next, we have to define our neural network as a class, and we will take two fully connected layers with bias, and we use the value activation function only after the first layer. So this is what we are doing here. We are defining our neural network model, and we have one layer with the input features is the number of pixels, in the case is 28, and the output is 28 times 28, and the output features is also the number of pixels. Then we have another layer. Again, we have the input features is the number of pixels, but the output features is the number of classes. And here we are defining our forward method. We have the first layer, then we have a relu applied to the output of the first layer, then we have the second layer, and we are returning the output of the second layer. Here we choose the size of the hidden layer, so the output of layer 1, the same as the number of pixels as the input, but it could also be a different number. So our program will plot the first 4 images of the training set, and for that we need to know the meaning of the indices. For instance, for the second image in the set, we will plot using imshow from pyplot, and then xtrain 1, 0, and we use the gray scale, a gray color map. So index 1 is the index of the image, and index 0 is for the current batch or set of images. So in our example, we only have batch 0, and then there are 2 remaining indices to the right, which are not seen here, are the image pixel indexes. So one example when we plot is we have here 4 digits, so this is how it looks like, and we see that we have from 0 to 28 pixels, 0 to 20 pixels, and it's a 3, a 9, and a 1. So after showing the images, we can reshape or flatten them into a one-dimensional arrays to make them suitable as input to our fully connected linear layers. So remember that the fully connected linear layers, they take only one-dimensional inputs. For that, we use the view function. So we are taking our images, that's 28 by 28, and they have this shape that we define, and we saw here 100, 128, and 28, and we are going to reshape using the view, and then here we see that the shape, the first element of the shape is the number of images in the batch, and we're putting this as an argument, and also the number of pixels is another argument for the view. You'll observe that we don't need to reshape the target because it is already a one-dimensional array with the correct classes. So after showing the images, the program is initialized in our neural network model with this part here, and then we will define the loss function using the cross entropy loss. The cross entropy loss is made for classification tasks, and it expects the data type as a torch flow tensor from the 10 outputs of our neural network, which fits, and long tensor as the data type for the target data, which also fits. And you can go to the PyTorch documentation and search the website for the cross entropy loss, which is here, and you can find more details about its definition. It basically first applies a softmax function to the 10 outputs of our neural network and turns them into probabilities such that they always sum up to 1. It also applies a logarithm because that is part of the cross entropy calculation, and to make the optimization more precise for very small values. It also turns the target data into probabilities of 10 classes. It assigns the correct class a probability of 1 and the incorrect class a probability of 0. Then it applies cross entropy to those 2 resulting probability distributions. The cross entropy gives a measure about how different 2 probability distributions are. So we see here that the cross entropy between 2 distributions, P of x and Q of x over classes x, is defined by this equation here. And we have a minus the sum, and we have a logarithm So here is the first distribution, the second distribution, and this is the cross entropy. It can be interpreted as the number of bits needed to describe a second probability distribution based on a first probability distribution. If they are identical, then we need 0 bits, and we minimize the cross entropy. Now, P of x is our target distribution, which is 1 for the correct class and 0 elsewhere. Hence, the sum degenerates to just a single summand for the correct class x equals to c, and it becomes minus log of the probability Q of c, where Q of c is the output of our network for the correct class C. And you can see more about this on the book Introduction to Deep Learning by Eugene Charniak from the MIT Press. Hence, after training or optimization, the probability distribution of our network after softmax should be as similar as possible to the distribution of the target. When we apply the trained network, which is called inference as opposed to train, instead of the softmax, we can simply take the argmax function, which returns the index with the largest output, or with the largest probability. So next, we will define the optimizer for the training, and in this case, we are going to use the ADAM. So, as before, ADAM is a popular and effective optimizer for neural networks, for adaptive moments, and it's a variation of stochastic gradient descent, and you can see more about the ADAM optimizer in this link here. So in our case, we will obtain a very fast optimization with only 10 epochs or iterations, with the decreasing loss function, for example, given here. Finally, we will compute the loss on our test set of 10 images, and we will see that it's clearly worse than our training set. So here we reached 0.14 loss in our training set, but from the test set we have 0.49, and we will also test the performance on an example image from the test set at inference using the argmax function. And it will show an image from the test set, and it will predict the corresponding class. So this is what we'll do. We will give it an image and we'll see what it predicts, what digit it's predicted. So this is just examples of one run. Remember that we are not using seeds for our random numbers in this case, so every time we run the experiment we will get different results because we have different initialization of weights and bias, and so you should also expect that you don't get these numbers. They're just illustrative for how we're going to build our PyTorch model. And then we see that we will give it an image, and the corresponding printout from the prediction in this case was 8. So the network is predicting the input image belonging to a class 8, and the image is usually correctly classified. And we see that in this case it is more or less easy for a human to identify as an 8, but I would not be surprised if somebody thinks it's a 9, or if the machine thinks it's a 9. So observe that the network always outputs a number for a digit, even when the image does not contain a digit. We can fix this introducing a class with a label noDigit, for which we also will need training data, which makes it difficult. Here is our complete PyTorch example. So this is taken by machinelearningmastery.com. This is a great source for examples and tutorials on machine learning, and it was translated to PyTorch and modified to a simply fully connected layer by Professor Shura. So here we are importing our libraries. We will use NumPy, PyPlot to plot, PyTorch, Torch Vision to have access to the MNIST dataset. Then here we are defining the neural network model, like we explained before. We are defining 2 layers, and we are using the ReLU activation after the first layer. So the input of the first layer, it will be the number of pixels. The output of the first layer also the number of pixels. The input of the second layer is the number of pixels. And the output of the second layer is the number of classes. Here we are setting the batch size for training, batch size for testing, and the number of classes. And the 10 classes are according to each digit, and we have digits from 0 to 9. At this point here, we are loading our data set using a data loader. So this is how we are doing this. So the normalize arguments, they are the mean and standard deviation. And here we also have now a train set and the test set. This is how we loaded our data set. Then we are also printing the shapes and the types of the data inside the data set. So here we're just doing an example, and we will plot 4 images. So we have this from the training set from 0 to 3. And this is what we are doing here. We are plotting these 4 images like here. So this could be a 1, a 7, a 9, and a 7. And we see that's 1, a 7, a 9, and a 7. So this is the type of the train. It's a float tensor. Type of the target. This is the input. This is the target. Here we have our shapes, like we discussed before, and here we can see all the classes of our target. So this is what we did this part here. Then we are doing that the number of pixels is the shapes, so it's 28 times 28. So it's the shape 2 and shape 3. So we remember that we have 100 was shape 0, then 1, 28, and 28. And this is what we are doing here. Then we are going to flatten the image, so we want not a 2-dimensional array 28 by 28, but we want a flat. And we can also, if needed, we can also normalize the inputs from 0 to 255 or from 0 to 1. But in this case, we are not doing this. It's not needed. Then we move on to build the model. Our model is this dense net that we defined here. We are defining our loss function that we are going to use the cross entropy loss, and we're defining our optimizer that we are going to use the ADAM optimizer. Here we are training the model. We're going to use just 10 epochs, just for a short example. And here we are doing the standard way, so we get the predictions, giving the input from the training data set to the model, and we have a loss, which is the predictions and the target. Between we compare the predictions and the target using the loss. Then we use the zero grad, we use the backward, and we use the optimizer step, as we're going to see in all PyTorch models. This is just a way to calculate the duration of the optimization, and then we'll move to the evaluation of the model. So again, we will see the loss on the test set calculated. Here we can save our model, and lastly we can do some inference. So it will predict an example in the digit test image, and we are going to see what image we are going to infer, and then we want to know what the model predicts. So this is when we run. This was the first part that I showed before. Now we see that we have the shape of the training set. Now it's 100 times 784, and we see the shape of the test, and it's 10 and 784. So this is the 28 times 28 pixels, and this is the number of images. So we have 100 in the training set and 10 in the testing set. Here are the losses for the training, and we see that it starts at 2.25 and it ends at the last 0.98, and it took 0.1 as the duration of the optimization. So it was very fast. And then we are going to give an example. So we, after the model is trained, we take an image, for example, from the test set, and in this case the prediction was correct. And here we can see the probabilities of all the classes, and why it chose 3, because we see that this is 0, 1, 2, 3, and 3 is the largest number of our of the probabilities here. So this is not actually the probabilities, because we use this cross entropy. So the probabilities here, they don't go from 0 to 1 and then don't sum up to 1 in this case. But we could also convert this using, for example, a softmax, and then we would have these as probabilities. And so that's it. First we saw how we would design our model, going through some important points, and here we went through the whole model and saw the results. At this point we'll test this case of an unknown image. We are using OpenCV, and we are generating a random image. So it's 28 pixels by 28 pixels, and we have an 8-bit unsigned integer, and we are saving this image. And here we will have two types of inference. So first we will use an image from the test set, and then we will import this randomly generated image, and then we will see what happens when we try to predict. So for the first picture, it's an image from the data set. It's a 3, and the prediction is correct, 3. But the second picture is an image that it's we cannot see, it's random numbers, but the model thinks it's a 0. So here we have the output, the predictions, and here what we did, we use a softmax function on these predictions, and now we have numbers that are probabilities. They go from 0 to 1 and they all add up to 1. We see that this 0 is the higher probability, but we can also put somewhere in the code, and we see that if the model is not confident enough, so if the probability is low, we can see and tell that's probably not a digit, and this is the case here. So we can set a threshold, for example, that if the model thinks has this probability of 70% for a certain digit, so we can assume that maybe it is a digit and the model can be correct. but in this case we have very low probabilities, and we can see that's probably not a digit. So that's it. It's a very simple example. There are many things that we didn't talk about here. There are many things that we just passed by very fast, but it's an example, a starting point on using the neural networks for classification. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schuller at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about neural network detector for the MNIST digit recognition. So let's get started. In the last part, in part 3, we saw how to use a classifier network for the MNIST digit recognition. At this time, we will change our strategy and we will use a detector for the MNIST digit recognition. In such case, it makes sense to use a detector as in part 1 for the recognition, because it has the advantage that we can train the recognizer of each digit class to output a 1 or a value close to it when it recognizes its digits, or a 0 or a value close to it when it's not recognizing its digit. If no digit is present, all detectors will output values close to 0, which is something that the classifier cannot do. For that, we are going to use the same neural network structure as in part 3 for the MNIST classifier, but with a different loss function. Instead of the cross entropy loss, we will use the mean squared error loss. But we need to take into account that the mean squared error loss expects a different target representation. For the cross entropy loss, we need the class label number as a target, which means we have one integer or a float input digit. The mean squared loss expects a float number for each class, which means 10 float numbers for each input digit, where the correct class should have a 1 and all other classes should have a 0. And then we can do this by initializing a torch array with zeros and setting it to 1 at the corresponding correct class, and this is called a one-hot representation. PyTorch has a function, it's the one-hot, that takes a long tensor with the index value of shape star and returns a tensor of shape star and num classes that have zeros everywhere except where the index of the last dimension matches the corresponding value of the input tensor. So it does exactly what we want to do. This is also an example from the machine learning mastery, but it was modified and then translated to PyTorch by Professor Schuller to use a simple fully connected network, and I further ported and modified to run inside Jupyter notebooks. We start importing our usual libraries, so we are using NumPy, PyPlot, PyTorch, Torch Vision, and here we are defining the neural network model, and we see that we are using a very similar structure as we used before. And we have two fully connected layers. The first layer has the input features equals to the number of pixels, the output features also equals to the number of pixels, and the second layer has the input features equals to the number of pixels and the output features as the number of classes, like we did before. This time here we are using a relu after the first layer, so we're using the relu activation function after the first layer, and then we have the second layer and we return the output of the second layer. At this part again we are using 100 images for the training set and 10 images for the testing set, we are also defining the 10 classes according to the 10 possible digits from 0 to 9. And this is the same what we've done in previous examples. So in the beginning, our example will print the one hot vector ytrain one hot, where we can see that each row contains the values for the 10 classes, and indeed only one entry is equal to 1 and all other are zeros. And this is what we are doing here. We are using the one hot function and we are converting the target to the one hot format. And here we see it was the original target 729908, and then here's the one hot format, and we see this is the first, so it's equivalent to 7, so 0 1 2 3 4 5 6 7, and there is 1 1 at the position. This is a 2, so 0 1 2, and so on. So now we've converted our target. It was a number, an integer that describes the digit, and now we are using the one hot format that also describes the digit, but we have a 1 at the position of the digit representation. Again, here we are flattening the images, so it was 28 times 20 by 28 pixels, and we have now 784 samples vector for each image. And we see that for our training set we have 100 vectors with 784 samples, and for the testing we have 10 vectors with 784 samples. So this is our training set and our testing set. We also did this before. Here we are defining our model using the network structure that we previously defined. Here we are using now the mean squared error loss, and the optimizer we still use the ADAM optimizer. At this point here we are training the network on the mean squared error loss using just 10 iterations like we did before. It's the same procedure here, and we have here the losses after every second epoch, and now we get also the final evaluation of the model. We get the loss on the test set. It's higher than the loss on the training set, as we expected and as we've seen before. At this point here we are doing the inference like we did also in previous examples. So we are feeding our model with an image from the testing set, and then the model will predict, at this time using the detector, which digit it is. So this is the image we are fitting, and it looks like an 8, and the detector predicted that it's, yes, indeed, it's an 8. And we can look here, these are the values for all the classes, and here is the value for 8, so is the highest value, and this is with the argmax. We pick the highest value and predicted the correct digit. So it's interesting to notice that now we have some values of the 10 classes, and we need to observe those numbers and we'll see if they show some confident detection. And finally, we are also feeding an image of random pixels as input, and we see that it's not a digit, but the prediction, our model thinks it's a 0, and if we see here, we have a value that is higher than this threshold for the confidence that we set, so the model thinks and predicts it to be a 0. So we need to be very careful in interpreting the results and setting correct thresholds. And of course, this is a very simple example, a very simple network architecture. We use just 10 iterations, but we can get a lot of interesting concepts and basic intuitions using this kind of simple examples. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about convolutional neural networks. Our idea is to look at convolutional neural networks under the signal processing perspective and compare it to filter banks. So let's get started. So far we used fully connected layers where the input is fully connected to each node in the following layer. Convolutional neural networks use a filter kernel instead, where each node is conducting a convolution like a filter. The filter kernel is also described as a receptive field of a certain size. At each position of this receptive field, an output is produced. Then it is shifted by a distance called stride, and a new output is produced, and so on. This has the advantage that the network is less dependent on the precise location of a signal to detect or recognize. There are convolution layers for 1, 2, and 3 dimensions. For the case of the MNIST digit recognition, we will use a 2D convolution, and it's defined as this class here in PyTorch, and you can take a look at the documentation of the conv2D that applies a 2D convolution over an input signal composed of several input planes. Here, padding means zero padding at the ends of the signal, for instance the boundary of our images. For padding equals to 0, only valid points are computed, which means that the kernel does not reach over the boundaries. For instance, if the kernel has a size of 3, we need a padding equals to 1 to obtain the same output size as the input. Here we implemented a convolutional neural network in PyTorch for the MNIST digit recognition task. So we see here we have two 2D convolutional layers, and then we have a fully connected layer at the end. For the loss function, we again will take the cross entropy loss, and for the optimizer we use ADAM. When we look, we can compare the convolutional neural networks with the case of our fully connected network that we used before for the same MNIST digit classification problem, and we will see that indeed we only have a fraction of the weights in our convolutional network when compared to the fully connected layer. This is an advantage for an implementation on smaller hardware. We can then train the convolutional network as before, and here we see a disadvantage. It takes much longer to train. We need over 1000 iterations or more to obtain a good solution, when compared to only about 10 iterations for the case when we use the fully connected network. So let's go through our model. Once again, we will import our Python packages and libraries. We are going to use PyTorch. We are going to use matplotlib to plot. Here we are defining the baseline model. So this is the convolutional neural network model that we are using: 2 conv2D layers, 1 fully connected layer. Then we have our activation functions. We are also using some max pooling. So what max pooling is doing is it's calculating the maximum or largest value in each patch of each feature map, and then the results are downsampled or pooled feature maps that highlight the most present feature in the patch. So not the average presence of the feature. In that case would be an average pooling, but you can take a look about max pooling also in PyTorch documentation. Then we are defining the batch sizes for our train, for test, the number of classes that we have. So basically it's the same procedure like we did previously, but now we just have a different model which is based on convolutional neural networks. Here we are loading our training set, we are loading our test set, and here we are just taking a look at some values just to make sure we load it correctly, and we are plotting, for example, 4 images of the a data set, and we have here a 5, a 0, a 4, and a 1, and we have the labels 5, 0, 4, and 1, and we've done this previously, so there's no new things here. Then we also build our model. We use the cross entropy loss, we use the ADAM optimizer, and then we train our model, and after training we can save the trained weights, and then we can, for example, test, and then we have here this image that it's for me it's a 5, but the prediction here tells it's a 9, so it's a wrong prediction, but in this case it's not really clear a 5, so there is a margin for interpretations and errors. If we run this cell again, and now choosing a different sample from the test set, and now we see that this is a 9 and the prediction is also a 9, so this was a correct prediction. We will now look at the 1D convolutional neural networks for audio processing, and we'll start with a 1D signal detector. We can use a one-dimensional convolutional neural network for audio processing, for example, to create matched filters and predictors as shown in lectures 13 and 14 of Advanced Signal Processing. So I put here the link to lecture 13 on matched filters and lecture 14 on prediction, and also the GitHub for our examples here. You can take a look. So we will construct a signal with a length 11, and this is what we are doing here. Then we can take a look at this signal. It's a ramp. We'll now add some noise and extend the length of our signal. So we added some noise and we also extended the length. Then we need to convert the signal into a PyTorch type. And we write a function signal to PyTorch for that case. Then we also can implement a filter similar to a matched filter using a one-dimensional convolutional layer, a conv1D, without bias and without a nonlinear activation function. For it, we need to specify a training signal, and here our signal to detect the ramp function x and the target signal y, which is the desired output of the convolutional layer, which the optimization should reach as closely as possible during the optimization or during training. So here we have our signal x and the target y, and observe that for the target y we specified a single peak, the 1, at the position the filter should detect the signal, and zeros everywhere else. This also leads to a minimization of the output outside the signal detection, which we didn't have in our closed form solution for a match filter, for example. And we will understand that more if you take these tutorials about match filter here. So we specify our convolutional detector layer given here, so the detector, and we have a convolutional 1D with a 1 input channel, 10 output channels, the kernel size 11, we use a stride of 1, padding equals to 10, and we set bias to false. Observe that here padding is equals to kernel size minus 1, which leads to a causal filter, meaning all its inputs are not in the filter. This implements our linear filter as a detector. The optimization we apply minimizes the mean square error, the so-called L2 loss function. and we let the optimization run on the same ramp function as before, and we will display the output of the detector with the clean and noise signal as input. So let's take a look at the code. We import PyTorch, we use matplotlib to plot. Also we may use NumPy. Here is the function to convert a signal vector as, like for example, a mono audio signal into a 3D tensor that the conv1D of PyTorch expects. Here we are defining the model with the convolutional layer, one-dimensional, with the properties, the parameters that we want. Here we're defining our input signal, is the ramp function, and also the target. Then we generate our model. We define our loss function as the mean squared error loss. We define our optimizer as an ADAM. Then we will train our model, and then we will generate predictions, and here the outputs. We see this is for the clean input and for the noisy input, and we see the peak is very prominent here. And here we see the weights. Here it was our input signal, so we have a ramp and the noisy signal. So the figure shows that the obtained weights or coefficients in PyTorch, they are used as a correlation instead of convolution, and hence the plot is the time reversed impulse response. Observe that it looks indeed different from our matched filter, which was simply the time reversed ramp signal. This is because the optimization also tries to minimize the output outside the detection time point. The result of detection for the clean and noise signals are shown here. And we can observe the peak at the detection time is indeed much more narrow than when compared to the matched filter. Our last example is an audio predictor. In this case, we are going to use the mean squared error as a minimization criteria for the loss function. In this case, this does not differ from the target of the closed form formulation, and hence we obtain almost the same solution. Here, the desired target signal Y is the audio input signal X, but one sample in the future. So what we can do is, for example, we remove the last samples of our audio signal as an input, and then the target would be our audio signal, but we remove the first sample for the signal to predict one sample in the future. So we import our Python libraries. We use again our vector to PyTorch. We define here the filter length equals to 12. Here we will have a convolution in one dimension. It's a very simple one, so we have one input channel, one output channel, kernel size equals to L, which is defined as 12, stride equals 1, dilatation is also equals to 1, defined here, and here we have the padding, that will be dilatation times the kernel minus 1. So what we do, we will import our audio file, and in this case is a rock and roll legend from AC/DC, Back in Black. We will normalize. We will only train, just to make it faster, we will shorten this audio, and we will train just this amount of samples. So here we are plotting our audio signal, the shortened version, and here we can listen to it. So this will be our input signal that we're going to use for training. Here we're generating our model with the mean squared error loss function. Again, we use the ADAM optimizer. We then train our model. We save the weights. And now we will process, after training, we will process the full audio Signal, so it's not the shortened version, but we use the full audio and we'll make predictions based on the obtained weights that were trained on the short audio. And this is what we are doing here. Here we are plotting the original and the prediction, so we see it here, and the prediction error. And here also we see the weights, and we can listen to the predictions. So this is a very basic and simple linear predictor that we're predicting one sample in the future. To finalize this tutorial, I leave you an exercise, and this exercise is to design a sampling rate up converter for an audio signal sampled at 8 kHz to a sampling rate of 32 kHz. For the training, we would generate the 8 kHz version by using a low-pass filtering and downsampling a 32 kHz version. So you can have, for example, audio samples taken from freesound.org. So the task is to design the low-pass filter as described, for example, in ADSP tutorial part 8, and also upsample it using this filter. So listen to the upsampled result and see if there is some audible artifacts, if there is not enough stop band attenuation. Then you can use a convolutional neural network to interpolate the missing samples, and you can use an autoencoder and decoder structure that it's present on the next set of slides. And then you will train it on audio signals, 8 kHz sample version as the input, and 32 kHz original as target. So on the next tutorials we'll talk about autoencoders, and you can then try this exercise. Then you'll just compare the result with the traditional upsampler using the low-pass filter and try to obtain better sounding results using neural networks. So this is an exercise that you can start thinking about it now, and by the end of this tutorial you can try it out. And here you can find a link to the tutorial on filters from Advanced Digital Signal Processing Part 8, and here the GitHub with Jupyter notebooks and interactive examples. So that's it for today, and see you next time. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schuller at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about convolutional autoencoder. So let's get started. A so-called autoencoder is a neural network with unsupervised training, which means that we don't need to supply a target function. There is only a training set, which is also the target set. A convolutional autoencoder uses convolutional neural networks. An autoencoder maps the input signal to a lower dimensional representation using its encoder part. In this way, it is similar, for instance, to an audio encoder, which compresses an audio signal into a representation with fewer bits than the original audio signal. I invite you to take a look at another course offered by Professor Schuller at the Ilmenau University of Technology. It's called Audio Coding. We also have many Jupyter notebooks and tutorials that you can find here on the GitHub and on a YouTube playlist. The decoder part of an autoencoder maps the lower dimensional representation back into the higher dimensional representation. And this is similar to an audio decoder, which decodes the compressed version back to an audio signal. The reconstruction after the decoder part should be as close as possible to the original. Hence, the original training set is also the target. In our PyTorch example, we simply use a 1D convolutional layer for the encoder, and this corresponds to the analysis filter bank of an audio encoder. And if you're interested to know about analysis filter banks, synthesis filter banks, and filter banks in general, we also offer a course. It's called Multi-Rate Signal Processing, offered by Professor Schuller at the Ilmenau University of Technology, and you can find, again, Jupyter notebooks with interactive examples and embedded video tutorials from our YouTube playlist. But going back here into this PyTorch example, where we use a 1D convolutional layer for the encoder, we also use an activation function. And in this case, we use the 10H function, which seems to work better than the sigmoid in this application, probably because it keeps the signs. We will use a stride or a downsampling factor of n equals to 1024 and filter kernels of size 2 times n. To obtain the same dimension as the input at the encoder output, which is a critical sampled filter bank, we need n filters or n output channels. But because we want to reduce the dimensionality after encoder, we choose a lower number, which makes it an over-critically sampled filter bank. For instance, with out channels equals to 32. This is similar to an audio coder where we simply drop the filter subbands with the highest frequencies. We will still have to choose the padding, meaning the number of zeros which we pad before and after our audio signal before the convolution, or rather correlation in PyTorch. To align the output of the decoder with the input signal for the case of symmetric filter kernels or impulse responses, we need a padding of the filter length divided by 2 minus 1, or the kernel size divided by 2 minus 1, because then the filtering starts with the first sample at the center of the filter, which corresponds to the position where the filter outputs the corresponding filter sample for both encoder and decoder. Hence, in Python, our encoder convolutional layer becomes this here. So we will have the number of in channels equals to 1, the number of out channels equals to 32, the kernel size equals to 2048, so it's 2n, the stride will be 1024, and padding will be the kernel size divided by 2 minus 1, and we use bias equals to true. Observe that we have one input channel, the audio signal, and 32 output channels, the subbands. For the decoder part, we need a synthesis filter bank, which in neural network literature is also called a transposed convolutional layer. And in PyTorch, we can use the conv transpose 1D. Therefore, we will have our conv transpose 1D that has in channels equals to 32, out channels equals to 1, the kernel size equals to 2048, the stride equals to 1024, and padding equals to 1023. So we can see that it's the same kernel size, the same kernel, and the same padding as we used for the conv1D. Observe that for the synthesis filter bank, we have 32 input channels, the subbands, and 1 output channel that will give us the reconstructed audio signal. The function for the encoder is now given here. So we will have our conv1D layer given here that we're calling conv1. Then we will use the 10H, like we mentioned before, and then we will return the output. Observe that here we included the 10H activation function, which can also be seen as a range limiter between -1 and 1. For the decoder, we have this function here, where the X reconstructed is the SYNCONV1 that is defined here as using this conv transpose 1D. For both together, it becomes the overall autoencoder. And we have the encoder, the decoder, and we will have the output is the reconstructed signal. We will put these functions into a class called ConvAutoencoder. For the training, we use the input signal also as a target. There, we have to limit the length to the signal length produced by the output model, which we can simply obtain by letting the model run once before the training. Here, y is the target signal with the same length as the output, the model output. As a loss function, a common choice is to use the mean squared error, even though it might not be optimal, but we will try out in this example. The training then can be done in a for loop, and we have a certain number of epochs, and then we will have the predictions generated by applying the model to our input. We calculate our loss, then we will just print the loss every epoch divided by 10, and then we will also need to, in every step, to use the zero grad into the optimizer. We use the backward to the loss, and we use this step into the optimizer. Here we have our full Python code. So first we will import the Python packages we are going to use. As usual, we are going to use PyTorch. We'll use matplotlib, pyplot to plot. We use librossa to handle audio, and numpy for other array operations. We can also use a GPU or a CPU. So if you have a GPU, or if you're running this using Google Colab, you can set your environment to use a GPU, and then you can run everything using the GPU. Another auxiliary function that we've been using before is this function to convert a signal vector X, like for example a mono audio signal, into the tensor prepared for the convolutional layer of PyTorch. Here is the class ConvAutoencoder that we mentioned before, where we set our layers. So we have the convolutional one-dimensional layer, we have the convolutional transpose one dimension, we set our encoder, our decoder, and then we have the forward that puts together the encoder and the decoder. Now we can load an audio, and in this case I'm going to use the legendary rock and roll AC/DC introduction of Back in Black, and we will use a stereo file that one channel, for example the left, will be used for training and the right will be used for testing, for example. So I am loading using librossa, then we are normalizing, so we have the amplitudes going from -1 to 1, and then we're applying our signal to PyTorch, and we have an X-train and an X-test that we're going to use later. Now we are generating our model, and we have here the loss function, that is the mean squared error loss. We also have the length of the signal at the output of the network. Then we set the target signal with the same length as the model output. And these are the parameters that we have. We generate our models, and we will have a total number of trainable parameters. We will have the length of the output then we set so the target and the input, they have the same length. Next, we set our optimizer, and we are going to use an ADAM with the learning rate starting with a 1 e to the power of -4, and then we can also save our weights that we've been doing before, but here we're just training using the X-train that we defined later, and as I explained, there is this for loop, and we go in using 10,000 epochs. So now the model is training, and we can see that it starts with the loss function very high, equals 0.01, and then it goes down to as low as 0.027 something. So after our model is trained, we can read the obtained weights, and we can also plot the encoder analysis filter and the decoder filters for subband 0, and also the encoder and decoder filter coefficients. And this is what we have here, the encoder and decoder filter coefficients. Then we can test our model on a training set. So we will have the predictions by applying the model, the training model, with the training set. And this way we have our predictions. And then we will have here the comparison between the predictions and the target. And this is what we have here, the target and predicted signal for one batch. Finally, we can listen to the result of the reconstructed signal. And it goes like this. So you can observe that there is a difference, an audible difference between the original file and the reconstructed, and it's clearly noisy. So in this way, the autoencoder can be seen as a kind of a filter. It learns a low-dimensional subspace from the training set. Every new input is mapped onto this subspace. And if it doesn't quite fit onto this subspace, major elements might be missing. So now if we apply the same model to the test set, so we split our original, it was on stereo, we use one channel for the training. Now we will use the other channel. We'll have predictions from this other channel, this X test, and we will also compare the predictions with the target. And this is what we have here. And we can also listen to it. And you clearly perceive that the reconstructed signal is much more noisier than we used with the training set. So the model was trained using this X-train data set, which was one channel of the audio, stereo audio signal that we had. And now if we're applying the same model that was trained only onto this training set, we apply a different input to the model, and we see that the output of the reconstructed is much more noisier. So we can clearly see how we train our model, it influences in terms of generalization to other signals. One more thing that we'll look at is the effect of signal shifts. So observe that the stride we used in our autoencoder. The stride corresponds to the down and up sampling rate of the corresponding filter bank. This sampling together with the convolution has the effect of processing the signal in blocks of size of the stride. If we now shift our input signal by prepending the number of stride zeros at the beginning, hence delaying it by stride samples, we will get the same blocks, just one block later. On the other hand, if we prepend a number of zeros which is not an integer multiple of the stride, the blocks will look different, and hence the result will look different, not just shifted. So for this example, we are going to test the trained autoencoder first with 100 zeros added at the beginning of the training signal. And we are using this constant pad 1D, so we are inserting 100 zeros on the beginning of this training. So we are giving a shift of 100 zeros, and then we are making predictions from this shifted input signal, and we can listen to it. We notice that the output appears really noisy. We will now shift not by 100, but by 1024. And this is related to the exact same number of strides. So we are now in this situation that we are shifting the input signal by prepending the number of stride zeros at the beginning, that is delaying it by stride number of samples. And this we are going to also listen. Well, let's compare. So pay attention now that we are using the same X train. So both use the X train, but first we are shifting by 100, and here we are shifting by 1024. And when we use the 1024, which is the same number as the stride, we notice that the noise added is much less. So we clearly see the effect of having these blocks starting on different points, how it affects the output of our model. So this behavior might be desired if a certain position or timing is important, but often is not desired. A straightforward remedy is to set stride, for example, with 1, but this leads to a much higher computational complexity for training and test or inference. As a compromise, we reduce the stride to a small value. For instance, for example, a stride equals to 16, and this has a lower complexity and not much audible shift sensitivity. And you can experiment if change in our model, you change the stride value both in the encoder and both on the decoder. So when we define our model here, if you change the stride values here, and you can change to two different values, for example 16, and then you compare and see what happens. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Shula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about the denoising autoencoder. So basically, the denoising autoencoder is the same as an autoencoder, but instead of having a clean audio signal as its input, it has a noisy version. Usually this noisy version has added noise, but it could also be other kinds of distortions. The goal of the denoising autoencoder is then to reconstruct the clean version of its input. Hence, it is trained on noisy signal as training sets. To avoid that the denoising autoencoder learns a specific instance of the noise, a new instance of the noise is generated for each epoch of the training process. In our example, we will use the same autoencoder structure as we used before, but we will train it with added noise. So what happens is that the training for loop will contain this expression here, where we are introducing some noise. Also, to make it shift invariant, we can also include a cyclic round robin shift as another type of distortion in the training loop. So for example, for the input and the input X and the target Y, we can have this shift of one to the right, like this round robin. So we will train trying to make it shift invariant. And then the training continues as usual for each epoch, and we have the zero gradient the optimizer, the loss backward, the optimizer step, and so on, like we've been doing before. So we will do two experiments. The first experiment we will use a stride of 512, and we will have some parameters of our autoencoder using 32 channels and a kernel size of 2048. And in the first experiment we will use a stride of 512, and on the second experiment we will reduce drastically this stride, and we will use a stride of 32. So for this first experiment we are using exactly the same code as we used before the previous tutorial, but with some modifications. So in this first experiment, these are the parameters we're going to use. We're using a number of input channels equals 1, output channels 32, kernel size of 2048, and a stride of 512. So this is for the analysis part, and this is for the synthesis part of our autoencoder. Here we are going to use the introduction of the classic rock and roll song by AC/DC, Back in Black, and we are going to use one channel, the left or right channel, to train, and the other channel to test, like we did in the previous example. We still use the same optimizer, the same loss function. We are using the mean squared error loss function. We are using the ADAM optimizer, and here is where things change. So here we are including this shift to the right, and it's also called this round robin, and we are also introducing a different noise for every epoch. So when we train, have this loss going down, we train many epochs, and here we are going to plot the encoder and the decoder filter coefficients for the subband 0, and this is what we have here, the same as we did in our previous tutorial. Now we are going to test our model using the training set, and this is what we are doing here. We are making some predictions, and here is the target and the predicted signal, and we can also listen to it. So here is the input, the model, and it was trained. So it is the introduction of Back in Black by AC/DC with added noise, and it would sound like this. The target is exactly this same audio file, but without the noise, and the prediction, the output of our model, is given here. observe that there is a bigger difference to the original signal, and the reconstructed version sounds very muffled. We can also test the model using a different file, so that file that was not used to train the model. So in this case is the other channel, so we used one channel to train, and we tested also our model with the training set. But now we are going to use a different, this is slightly different as it's the same song, but we are taking the other channel, and this is what we are doing here. Here is the original and the predicted signal, and we can also listen. So here is the input of the model. So we can hear that the noise is there. So this is we added this noise on purpose to train our model. And here is the output of the model, so the reconstructed. So this model never seen this file before. Of course, it's seen a very similar version of this file, which is the left channel or the right channel. But this is just for learning purposes. So you would use thousands of different audio files, play around with different hyperparameters and network architectures. But this is what we have for this tutorial. It's a starting point, and this is first experiment using a stride of 512. And we see that the noise is less present, but it also sounds very muffled. Here's the input with noise. So the denoise is more or less working, but the output is very muffled. So we also see that the shift sensitivity is not there anymore because of the way we trained. So here in the test version, so we are using the test for verification, and we are adding a shift of 100 samples. So this is what we're doing here, and we are also adding some noise here. So what we do is that we take, for training, we used one channel of a stereo audio file. So let's say we use the left channel. We added some noise and we trained our model, and we included this round robin. So we included this shift during epochs to try to minimize this shift and to have minimize the shift sensitivity. And it seems that we achieved this because when we are testing our model using a verification set, so it's a different audio file. So we trained with the left channel, now we're testing with the right channel, and we are adding here 100 sample shift, and we are also adding some noise. So the next experiment, we're going to change just the stride. That means that we're reducing the downsampling and upsampling factor. So before we used 512, and now we are using 32. And you see that now the number of subbands is equal to the n factor for downsampling and upsampling. So we have 32 output channels. We have the same kernel size as before, but we have now stride equals to 32, and we will try to see what happens. So basically now we are processing more data as our strides are much smaller. So the model is exactly the same. We just changed the stride value, and we will do the same thing. So it's the same audio, for training and for testing, everything stays the same. We still have this round robin with the shift by 1 to the right. We are adding noise for training, but now you will notice that it trains or it optimizes much slower than before, because now it has to process much more data. And here again we're plotting the encoder and decoder filter coefficients, and here we will test our model using the training file. So here we have the target and the predicted signal, and we can listen to it. So this is the same as before. There is no change on the training file, apart that we are adding different noise every epoch. So we see the noise there, and now the reconstructed signal, so the output of our model, and we have so it is a bit denoised, so we perceive less noise than the original, the input to our model, and it's now less muffled than before. So if we compare this with the experiment where we used 512, the stride of 512. So it's less muffled. And here we can also do the same for the validation, so our verification, not using the same file as we trained, but using a different file. Here we have our reconstructed. And here was the original and the input of the model. So we can perceive more noise So it seems that our denoising autoencoder is working, and we can also change parameters, change hyperparameters, change the network structure, and try to achieve better results. And of course, you would need to use very good and big data set to achieve a good autoencoder, denoising autoencoder. So we see that when the model is finally trained, we can hear that the signals indeed sound a bit better and less muffled. And this also shows the effect of the stride. So too low, it means there will be a long training, and too high, we will obtain less quality in this case. So that's it for this tutorial, and we will continue with more on machine learning for audio signals in Python next time. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about variational autoencoders. So the denoising autoencoder that we saw last time was robust against noise at its input. It was the audio signal. This time the variational autoencoder is robust against noise in its encoded domain, what is also called the latent representation in the latent space. Here you can find a very nice tutorial about what is a variational autoencoder. There are very interesting explanations, and also here at this link you also find another very interesting tutorial understanding variational autoencoders. Similar to the denoising autoencoder, we also add a fixed noise during the training process, but instead to introduce noise at the input, we add it to the encoded signal in the latent space. But the training could just find a solution where the latent representation just becomes very big, which would effectively drown out the noise because it would appear relatively smaller. To counteract this, we introduce a regularizer term, which is added to the reconstruction loss function, usually the mean squared error. This is an added term for the loss function, usually with a factor for weighting the importance of the regularizer. This regularizer term is minimized if the mean value, meaning the output of our original autoencoder, is minimized. This punishes large values in the encoded domain and keeps the small in the training. We could now just train this network in this way. But to help the training, there is a parallel network which outputs the variance of the added noise for each element of the encoded signal in the latent space. In this way, the training can start with very little noise to help the training find a useful and suitable representation. To avoid the system staying in the no-noise state, there is an additional component in the regularizing term, which is minimized if the added noise has unit variance, meaning a variance of value 1 for each component of the encoded latent representation. This effectively punishes too little or too much noise. Too little more than too much. Hence, for this regularizer term, we need a measure for how different the current noise distribution is from the desired Gaussian noise distribution with zero mean and unit variance. Let the current mean from our usual autoencoder be mu and the current standard deviation to be sigma. In Bayesian terms, this is called the posterior distribution or the observed distribution. These are vectors of the size of the dimension of our latent space, meaning each element of the output vector x of the encoder has its own mean and standard deviation. Then our current noise probability distribution is given by this equation here, where we have our mu and we have our sigma. In our case, the division by the standard deviation vector above is an element-wise division, meaning we don't take into account cross correlations. Our desired probability distribution with sigma equals to 1 and mu equals to 0 is given here. And this is also called the prior distribution or the assumed distribution. A common information theoretic measure of how different two distributions P of x and Q of x is the Kubeck-Leibler divergency or the KL divergency, and it's given by this equation here. And you can read more about the Kubeck-Leibler divergency here, and it's a measure of how one probability distribution is different from a second reference probability distribution. Because we assume that the distributions of the different elements of our distributions are uncorrelated, we can simply sum up or average the Kubeck-Leibler divergence of each element in the latent space, and our variational loss VL becomes this equation here, where P of j is the probability P and K of j is the probability K. According to the Appendix B of the paper Autoencoding Variational Bayes from Kingma and Welling, that you can find in this link here, the variational loss becomes this equation that we can implement in PyTorch and Python. And when we compare this to a simple mean squared error function to our ideal of mu equals to 0 and sigma equals to 1, and we have this plot here. In this case, we have the standard deviation ranging from 0 to 2, and we have the mu equals to 0, and we will have this plot here where we can see the standard variational autoencoder loss and the mean square distance from the ideal loss. Here we can see that both loss functions have the same minimum at sigma equals to 1 as expected, even here. But we see that the standard variational autoencoder loss has a steeper increase towards lower variance and less increase to higher variances. This means that low variance, the case of less noise, is more punished by the standard variational autoencoder loss. Hence, the training will be less likely to find a low noise solution. Our model now will have two network outputs to train. The Y encoder mean, which corresponds to our previous encoder, and the Y encoder standard deviation, which just produces the currently allowable standard deviation for each mean output during the training process. Since now our loss function consists of two components, we combine them in the training loop using a Lagrange multiplier to combine them in an overall loss value. And you can read more about the Lagrange multiplier here. Basically, the Lagrange multiplier simply weights the two components to achieve a desired trade-off between them. In our case, it will look like this. So we will have our mean squared error loss plus the variational loss with a factor of 0.01 in our case, and this is our Lagrange multiplier. Here we also see that we can choose between two mentioned variational losses. So we have the variational loss and also the variational loss 2, that is the mean squared distance from above, and the standard variational autoencoder loss. In our experiments, the program will read in two speech files as a simple training set. It is read in such a way that each file is one batch, and we use the signal to PyTorch function to convert our arrays into PyTorch tensors. Here we can define the actual autoencoder. So we have here the analysis filter bank for the mean values, and then for the standard deviation values, and then the synthesis filter bank. So we have here self conv1 mean, and we will use 32 output channels, kernel size of 8 times 2048, and the stride of 8 times 1024. For the standard deviation values, we use the same characteristics, so it's 32 channels, 8 times 2048 for the kernel size, and 8 times 1024 for the stride. This will be this convolutional layer for the standard deviation values. Then we have the synthesis filter bank, and we are using the convolutional transpose 1D. Then we have our encoder mean. We are also using the tanh as activation functions. So remember that our values will be from -1 to 1. Then we have the encoder standard deviation, and in this case we are having an absolute value together with the tanh, so now we will only have positive values. This is for the analysis. Then we have the decoder, and we have our forward method, and here we see that we also have this part here where we are adding the Y encoder mean plus the Y encoder standard deviation, and we're multiplying by this torch rand and like function. and we are going to talk about this later. Observe that the autoencoder uses filter kernel sizes of 8 times 2048 and strides of 8 times 1024, but we only use 32 channels. And this means that we have a very tight bottleneck here. The factor 8 here is just for experimentation, and you can replace it by 1, for example. Then we would have shorter filters, shorter strides, and the bottleneck becomes less tight, but the results will be much more noisy. And in addition to our previous encoder, which here we call the conv1 mean, there is also the encoder for the standard deviation of the added noise in the encoded domain that we're calling conv1 std. Like I explained here before, we have the conv1 mean and the conv1
Here
std
is the
torch rand and like, and it returns a tensor with the same size as input that is filled with random numbers from a normal distribution with zero mean and unit variance. And this is what we are using here for this Y variational. So now we'll go through the full code for the variations. We encode the Py, matplotlib, pyplot. We are importing our PyTorch. And we can also use the scipy.io WAV file to read in audio files. And we are also going to use librosa if we will use MP3 files. Here is the function signal to PyTorch that converts a signal vector, for example, like a mono audio signal, into a 3D tensor. Here is the definition of our model, the conv autoenc that we talked earlier, and we have our encoder mean, our encoder standard deviation, our decoder, our forward, and here we have our loss functions. So we are going to experiment with two different loss functions. So we have our variational loss that returns the variational loss from arguments mean and standard deviation, and you can see it from the paper autoencoding variational base. That was the equation that we talked before, but also we can have an alternative that is the mean square distance from the ideal, mu equals to 0 and sigma equals to 1, that is given here. So here we are preparing our training set. So we're going to use the famous speech from the introduction of Iron Maiden, The Number of the Beast, and also the speech from Iron Maiden, Ace is High. So we're just preparing here. Will be the batch 0 is one file, batch 1 is the other file. We do some normalization, we convert to PyTorch tensors, we generate our model, and we define the loss function, the part that is the mean squared error. And then we are here. So we have this part ready. Here we are defining also our optimizer. So we are using the ADAM optimizer with a learning rate of 1e to the power of -4. And then we can start our experiments. We've seen the theory, we defined our model, we looked at the variational losses, so we have everything to start running a few experiments. So the experiment number 1, we will run like a conventional variational autoencoder. So here we will use our variational loss, not the alternative one. We have here the Lagrange multiplier. So our loss is the mean squared error plus 0.01 times the variational loss that we've defined earlier. We have here our standard deviation values from the network and the mean values from the encoder network. Then we are multiplying the standard deviation by this function rand and like that we've seen before. And we add to the Y encoder mean, this is the Y variation, and then we apply this, we apply the model of the decoder to this Y variation, then we have our Y predictions. So we'll train our model, and after training we have here our weights, and we have the plots of the encoder and the decoder filter coefficients. We can see here. So after training the program, we have the weights of the autoencoder and the decoder. We have the coefficients in the encoded domain, and then the added noise controlled by the encoder STD network. So here we will also see that we will run our experiment first without the additional noise and then with added noise. So here we have our training set, and we have our no noise case, and we have here the noise case where we're adding Gaussian noise with unit standard deviation to the encoded signal, and we infer and make some predictions, and then we will also listen to the results. So first is the training set output for the clean encoded signal for batch 0. So remember, we have two audio files. One is the batch 0, another one is the batch 1. So this is the training set output for the clean encoded signal.
Let him who hath understanding reckon the number.
So we see there is a bit noise there, but the noise has some special characteristics. We will discuss more about this a bit later. And now is the training set output for noisy encoded signal for the same file. So we see it's very noisy, but the noise somehow resembles the original audio file. And this also is a characteristic that variational autoencoder, they also have the potential to be used in generative applications. So when we want to generate certain sounds, for example. Here is for the batch 1, so it's another audio file. Then again, for the clean encoded signal,
we shall fight with growing confidence and growing strength in the air. We shall defend.
So we see that there's a bit of noise in the background, and the noise also has these characteristics that it's similar to somehow the speeches of the training set. And now this is the training set output for noisy encoded signal.
We shall fight with growing confidence and growing strength in the air. We shall defend.
So we see that there is a lot of noise. We added noise, but we can still hear the original output. And we see that because we used the variational loss that penalizes, like we discussed before, it penalizes noise, for example. And here we see that we will have the standard deviation closer to 1. Here is the target and the noise predicted signal for batch 0. Here's in the coded domain for batch 1. So those files were what we use for training, but we also have another file for validation, another signal that it's the same files, but I'm just taking it's a long speech and I'm taking parts of it. So the first one was the ACES high we used with a certain offset, but now we are using no offset. You listen that it sounds a bit different, so it will play the validation signal without and with noise, but we will see that the model is now less robust to noise, as now is the validation, so the model never seen this signal before. And we will also make a test when we will infer pure noise on the input, and there is no audio file or speech, it's just pure noise, and we will see and listen what happens in this case. So here is the case where the verification set, this is the input, so this is not the output of the model, there is no added noise. This is what we are using as an input to the variational autoencoder.
We shall go on to the end. We shall fight in France. We shall fight on the sea.
So this is the classic introduction of ACES high from Iron Maiden. And now we will see the output of the model for the clean encoded signal. We observe that there is a lot of noise, but the noise also has this interesting shape and interesting sounding characteristics. Now we added the noise, so the verification set output for the noisy encoded signal. We almost cannot hear anymore the original, and this is the case when only noise as encoded signal as we are using as an input to the model. So we are feeding this model just with noise, and this is what it sounds like, the output of the model. Here we see the verification, so it's the original and the predicted signal. And you'll notice that we have much less robust to noise, and we see that we don't achieve good results. Just remember again that this is just for learning and studying purposes. We're just using 2 small audio files for training, but we already can have a lot of intuition about variational autoencoder, and also to take a look of some of its characteristics. In the experiment number 2, we use our alternative variational loss function for the training. So everything stays the same, but here we are commenting this loss that we used before, and now we are using the alternative variational loss, and everything stays the same. So we will train our model, and then here is the encoder and decoder filter coefficients. Here again we will be able to listen to the results. So we will observe also that the standard deviation is less close to 1 because this loss punished the lower noise values less. So the autoencoder should be more sensitive to noise now, and even the clean version would be not so clean. So this is also, we are testing with the training set, so it's the same audio files that were used to train the model, and we'll listen.
Who have understand.
So this is the clean encoded signal for batch 0, and we already notice more noise there, and now it's the noisy encoded signal. So there's a lot of noise going on there. The noise also has this interesting shape and characteristics that are somehow similar to the audio files that were used to train the model, but we also see that the model is less robust to noise. So here is the output for the clean encoded signal for batch 1, so it's a different audio file.
We shall fight with growing confidence and growing strength in the air. We shall defend.
So there's a bit of noise in the background, and now the output for the noisy encoded signal.
We shall fight with growing confidence and growing strength in the air. We shall defend.
Oh, it's interesting to note also that the model is kind of behaving better on this batch 1 than on the first batch 0.
Who have understand.
And it's very interesting to note this noise shape and characteristic and similarities with the audio used for training. So once again, we also will test on the verification set. So this is the input of the model without any noise.
We shall go on to the end. We shall fight in France. We shall fight on the sea.
This is the output for the clean encoded signal. Very interesting output. And this is the output for the noisy encoded signal. And this is the output when we only use noise as encoded signal. And here again is the original and predicted signal. So we see that in many cases, when we add a lot of noise or we use pure noise in input, the model output produces a mix, a strange mix of the training set speech pieces. This is the last experiment. This is experiment number 3, and this time we will only use fixed noise with unit standard variance in the training process. So this means that we will not need the variational loss anymore. So our Lagrange multiplier now will become 0. So all this will be 0, and we will have just the mean squared error. And now our Y encoded standard deviation will be ones with the same shape of the mean. So everything stays the same. We are using the same training set with the same audio files. But here instead of using the standard deviation values from the network, we are using the unit standard deviation. And also here we are setting the Lagrange multiplier to 0. So our loss is just the mean squared error. So we will train the model, and it will be exactly the same procedures like we did in the other experiments. And then we have also the weights and the encoder and decoder filter coefficients, and we already notice this very prominent analysis filter 0 for the STD. And here now we will test using the audio files from the training set. Listen now, so this will be the output for the clean encoded signal.
Let him who hath understanding reckon the number.
Here is the output for the noisy encoded signal. And here for the batch 1, so the other audio file.
We shall fight with growing confidence and growing strength in the air. We shall defend.
And here is the training set for noisy encoded. So we added noise for the previous audio file, the same as this one, so it's batch 1.
We shall fight with growing confidence and growing strength in the air. We shall defend.
We see there's a lot of noise in the background, but we can still understand the original file. And we see also that the standard deviation now is a constant 1. And here we have the target and the predicted signal for batch 0, for batch 1, and we see that after training we have the plot with the added noise, so that it's indeed a constant 1 like we seen before. And the playing back the clean signal, we can hear that this sounds somehow less clean than the first experiment perhaps. So it seems to be more robust against noise in the encoded domain, or at least for the files used for training the model. But now we will do again with a verification set. So this is a part of the audio that the model never seen. So this is the input.
We shall go on to the end. We shall fight in France. We shall fight on the sea.
This is with the clean encoded signal. And here is with added noise, so the noisy encoded signal. And here when we use only noise as the input. And here we have the original in blue and the predicted in orange. So again, we see that in both cases it produces a mix of the training set speech pieces. So with noisy encoded, and we use just noise as the input. And we have to keep in mind that in this last case, it has the advantage that it does not need a neural network for the standard deviation prediction. So what we did is just we set it to a constant standard deviation to 1. So that's it for this tutorial. This is a very basic and short introduction to variational autoencoders. It's more to give some insights and intuition and to start to understand the basics, the theory behind it. And I encourage you to explore more other tutorials that are available online and play around with bigger data sets and experiment with different network architectures, different hyperparameters depending on the problem you're trying to solve. And I see you next time. Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Shula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about recurrent neural networks. So far we saw networks that process the input in layers towards the output, but with no feedback path. Recurrent neural networks compute an internal state from the input, which then becomes part of the input in the next time step. This makes it similar to an infinite impulse response linear field, which have a feedback path via delay elements from their output back to their input, as shown in the following picture. Here we have for input x of n, we have some delay elements, we have some gay elements, we have some addition, and here we have our output, and the output goes back here. There are some more delay elements and some more additions, and so there is a feedback loop. This is a generic infinite impulse response filter, and you can take a look more in detail in the lecture Advanced Digital Signal Processing, slide 7. It's also offered by Professor Shula at the Ilmenau University of Technology, and also there's a reference book that's Discrete Time Signal Processing by Oppenheim. And here we also have another tutorial from the Advanced Digital Signal Processing part 7 about filters. And this is the part about infinite impulse response filters. We'll first analyze this structure, and then we will try to implement it with a recurrent neural network. What we'll try to do is to analyze this IIR filter structure, and we'll try to compare it and implement it using a recurrent neural network. The coefficients BI are the feed-forward coefficients, and the AI are the feedback coefficients. Xn is the audio input signal, and Y of n is the output signal of the filter. Because of the feedback path, the IIR filter can start to oscillate and even to become unstable. And this happens if the poles of its transfer function in the z-domain are outside the unit circle. But when the poles are just inside the unit circle and close to it, this filter produces an impulse response of decaying oscillations or sinusoidal signals. As an audio signal, this can sound like a tone from a bell, for example, and in this way it can be used to generate a signal. So the corresponding difference equation in the time domain is given here by this equation 1, and we have our output, we have our input, we have our B coefficients, and we have our A coefficient. You can also take a look at the book by Oppenheim, the discrete time signal processing, on chapter 6 from the 1989 edition. Then when we take the transfer function of this difference equation, so the resulting transfer function in the z-domain, you can also take a look at the lecture mentioned here, so in order to understand difference equations and also the transfer function in the z-domain, and this becomes the resulting transfer function is given here. For our test generative example, we would like to have a decaying sinusoidal function as an impulse response. And we obtain this from a simple second order IIR filter with the B0 equals to 1 and 0 elsewhere for L equals to 1 and R equals to 2, meaning just 2 feedback delays and coefficients. Then we have this equation number 2 here. So we are setting B0 equals to 1, 0 elsewhere, L equals to 1, and R equals to 2. And the resulting transfer function in the z-domain is then given here. And now we notice very interesting things here. The denominator polynomial is of order 2, and hence it has 2 zeros, which result in also 2 poles, P0 and P1 of the transfer function h of z. Each pole causes an oscillation at a frequency which is given by its angle to the real axis in radians, where pi is equal to 180 degrees, interpreted as normalized frequency, where 2 pi corresponds to the sampling frequency. If we want a real valued oscillation, we need a conjugate complex pole pair. So let's try to look at an example to make it a bit more practical and to understand a bit more the theory. What we want is that we want a decaying oscillation as an impulse response with a frequency of 440 Hz, which is a musical pitch A, at a sampling frequency of 8,000 samples per second, and a decay factor of Q equals to 0.995%. So the normalized frequency will be then 2 pi times 440 divided by our sampling frequency divided by 8,000. And then we'll have the conjugate complex pole pairs given by Q, which was calculated here, times the exponential of plus or minus j, the imaginary number, times Q. So let's use Python to have these poles. So I'm using a NumPy for mathematical operations and PyPlot, matplotlib for plotting. So we are defining our Q, because in here is part of the formulation of our problem. Then we are calculating omega. It's given by this equation here, and then we have our conjugate complex pole pair given here with plus or minus j times q exponential, and then just using an interesting approach from matplotlib to plot the unit circle, and also having here the complex z-plane with the real axis and the imaginary axis, and we have here our poles. They are symmetric, because they are, of course, as defined here, conjugate complex. So with these poles, the transfer function now will become this equation given here. And we have here now, we have our poles P0, P1, and when we compare with the formula of our transfer function in the z-domain, and we can see that A1 is equal to adding the poles, and A2 is a multiplication of the poles. If we use the above pole pair, and reminding the Euler's formula that e to the power of j omega is equal to the cosine of omega plus j times the sine of omega, and this becomes a1 is 2q times the cosine of omega, and a2 is minus omega squared. Here we will continue using Python. First we will create an impulse, meaning there is a 1. We will multiply this 1 by a factor, and we'll make it 0.1 to keep the signal smaller, followed by as many zeros as we would like to produce for the impulse response. Then we will use a SciPy signal L filter to generate the impulse response. So there we need to observe that the L filter function expects the A coefficients, and here it will be called the K coefficients, with opposite sign. So what we're doing here, we are importing signal from the SciPy. We're defining our sampling frequency. We are defining the length of our sequence as 2 times the sampling frequency, so be 2 seconds. Then we are calculating again our omega, and then we're having k1 and k2, because now it's given by these, what we previously called a1 and a2 from this transfer function here, just calling k1 ak2. Then we are building our impulse, so we start with zeros with the length of the sequence length, and we add a value at position 0. Here it's 0.1. As mentioned before, we want to keep the signal smaller. We can then play back the resulting impulse response to our audio output. We are using the IPython display audio function. Here's our filter. Here we're filtering using the L filter, and then we have here our array, and remember that we just told that the filter expects the A coefficients with opposite sign. We have here minus k1 minus k2. So it should sound like this. Observe that it indeed sounds like a small bell or a xylophone or some kind of a percussive metal oscillating instrument in this category of bells and xylophones. So first we used our infinite impulse response filters to generate this impulse response, but now what we're going to do is to implement using a recurrent neural network, also called RNN. In IIR filters, we have the delay chain of delay elements c to the power of -1, which delay each sample by 1 sample interval. In a recursive neural network, instead, we have the hidden states h, which is a vector or an array which is updated after each sample interval according to the matrix equation given here. So we have a tanh function here, we have some weights, we have some coefficients. So x of t is our input signal, here the impulse. T is our integer valued time index, which was n for the IIR filter. Then we have W, that are weight matrices. We have these coefficients B, which are the biases, and we will not use them. We don't need them for our purpose. Observe that x and h, they are column vectors or arrays. And also we have the nonlinearity. By default is the 10h function, but it can, as an alternative to the relo function, that can also be used. And here from PyTorch documentation, you have a class recursive neural networks that will apply multi-layer Elman RNN with tanh or relo. Can be also used as an alternative. And for each element in the input sequence, each layer computes the following function, which we have it here. You can read more. Very important to understand the documentation, implement things. Since our IIR filter does not have a nonlinearity, we choose the tanh function and keep the signal small such that it stays in its more linear region. So you're familiar with the tanh, so the function that goes from -1 to 1, and it will so values that are bigger than 1 or smaller than -1, they will be, let's call it, shaped to this tanh function. But if we keep the signal small enough, it will stay in its more linear region and we will avoid some problems. The hidden state H also represents the output of the recurrent neural network. So to make it function like our IIR filter, we use the hidden states as the delay line in our IIR filter, which means that the hidden states are equal to the filter output and its two delayed versions. So here we have this equation here, hence I equals to 0 denotes the most recent sample. And we have I going from 0 to 2, so we have values for I equals to 0, 1, and 2, and I0 denotes the most recent sample. Observe the notation ht of I, and this is an array or a column vector with 3 entries indexed with I at time t. From the time domain difference equation number 2 that we saw earlier, we know this here, which is equal to this one here. So then we have now relationship between the output, we have our input, here we have this hidden state h t. The h of t of 0 is equal to the I of t is equal to x of t plus a coefficient a1 times y of t minus 1 plus a2 times y of t minus 2. And then we have this equation here now without the y of t, but we have the ht of 0. Then we just need to shift the remaining hidden states by 1 time step down such that they become the delay line. So ht of 1, it will be equal to h of t minus 1 of 0, and ht of 2 will be ht minus 1 of 1. So now, with those equations in hand, we have the necessary weight matrices w of hh and w of ih. In our simplified recurrent neural network update equation becomes this here, where we neglected the nonlinear activation function and we set the biases to 0. From here, we are now here. Then we will get our weight matrix w of hh, and we have a1 here, a2, 1, 1, and zeros elsewhere. So we set x of t as the single sample x of t instead of a column vector, since we don't need past x values because we chose no IFIR part with L equals to 0 in equation 1. Hence, W of IH just becomes a column weight vector which has a 1 in the position for HT of 0. I have here the WI of H. And this is now our recurrent neural network working as our III filter. So the output of our recurrent neural network IIR filter is HT of 0, which we obtain by adding a linear output layer which has a factor of 1 for this element and zeros for the other elements. So now we will use PyTorch and do a complete implementation to have this IIR filter implemented as a recurrent neural network. So we import here PyTorch. We will define some parameters. So the in features equals to 1 is the samples per input time step. Hidden size is the number of hidden states, so the memory elements we are going to use, and we are setting it to 3 as we discussed previously. Outputs is equals to 1, so this is samples per output time step. Then we decide the number of layers, so we'll use 1 layer, and we will set batch equals to 1. We also been using many times this functions. There are many ways how we can do this. We've been using the signal to PyTorch, which converts our audio signal to the PyTorch format for the recurrent neural network. Then we compute the coefficients for our IIR filter like we did before. And this is exactly what we did before. So we see it also sounds the same. There's no news here. But we will use these coefficients as weights. So we will replace, for example, values in our weight matrices by these coefficients that we calculated in a way that our recurrent neural network will work as an IIR filter. And here we see, for example, that we have the recurrent neural network as IR filter. So the hidden states H as delay chain, waits for updating, H for shifting the delay line, and this is what we also saw previously. So for example, if A1 is equal to 2 and A2 is equal to 3, then our array will become, there is this array here, 1, 2, 3, 0, 1, 0, and 0, 0, 1. We can first apply a shift operator S and then the coefficients H multiplied from the right. So we are doing a dot A times dot product of A and S. We have our S array given here, we have our A array here. This will be the resulting matrix, and this is the W H of H. So we will have here 2, 3, 0, 1, 0, 0, 1, 0, 0. Looks very similar to this here. A1, A2, 0, 1, 0, 0, 0, 1, 0. Now we can create our neural network model and assign our desired weights such that it acts like our IIR filter. So pay attention here that we are not training this moment, so we are just using the architecture of a recurrent neural network to behave like an infinite impulse response filter. So we will, when we create our network model, we will assign our desired weights. And this is what we are doing here. And we have here our K1, our K2. So we are taking this weights, and then we are assigning the weights that we want to the proper position in the weight matrix. So with the Spring function, you should check at runtime if the weights of the model now look like what we expect. And if they look okay, we have now a functional neural network which should work similar to an IIR filter. And we can then, for example, convert our impulse to PyTorch and then feed it to our neural network. What we're doing here, we have our impulse here, our impulse, then we're converting to PyTorch, and then we are feeding our neural network model with this signal, and this will give us the output signal. And the output of the recurrent neural network is then converted back to NumPy, so we can play it back to the speaker for listening comparison, and we can also plot together with the output of the IIR filter for visual inspection and visual comparison. So this is what we're doing here. So remember that now this is the output of our recurrent neural network, and it sounds like this. And it sounds exactly the same as from the IIR filter. And here we can also see visually, so this in blue we have the IIR filter impulse response. It would be, let's call it our target, and the output of the recurrent neural network. And see there is the same shape, apart from that the output from the RNN is somewhat smaller, and this is because of the 10H function. And this shows that a recurrent neural network can be indeed set up to function like an IIR filter. And this creates an interesting connection between recurrent neural networks and infinite impulse response filters, and hence RNNs can be viewed as a generalization of IIR filters. So previously we assigned the desired weights to our network model, our recurrent neural network model. We had decided, we calculated the weights so it would behave like an infinite impulse response filter, but also we can do more with it. So now we know that there is a solution for the weights that make the RNN behave similar to an IIR filter. And in general, we will not pre-compute the weights, but we will let the optimization algorithm to figure it out on its own, given the impulse as training input, desired impulse response as the target signal. So we will use the impulse as the training input and the desired impulse response as the target signal. So if the optimization is powerful enough, it should be able to find the solution. But we have a problem. The problem here is that for a system with feedback as the recurrent neural network, the gradient of the loss function for the optimization is very difficult to compute. As we know, PyTorch uses the AutoGrad to compute the gradients of the loss function. You can see here some documentation about the AutoGrad, so this automatic differentiation, and how, and here more information about this AutoGrad. Also here you can understand the heart of the PyTorch computations, is this automatic differentiation. And the weights, they are of type Torch tensor. We have the attribute called requires grad, and we can set it to true or false. So The PyTorch then tracks all operations with the tensors to be able to quickly do the gradient calculation using backpropagation. Backpropagation is basically just another name of the chain rule of differentiation. And this is done with the backward step in the optimization loop, and the resulting gradient is then stored in the grad attribute. So when we have a feedback loop, as in a recurrent neural network, we apply the network over and over again to its output. And this can be seen as a very deep neural network where each loop iteration is another layer with the same coefficients. Applying backpropagation means that we go back through all those layers or all those iterations using the chain rule for the computation of the gradient. But each computation introduces computation errors, which then will accumulate. If our impulse response signal decays very slowly, then we have significant components far back in history, which makes the computation of the gradient very inaccurate. This can also lead to the problem of vanishing gradients, where very small values are rounded to zero, or exploding gradients, which leads to not a number errors, also this NAN. Our example has an impulse response with significant values over several thousand samples, but at k equals to 0.995 and it still converges. But if we make it a little longer by increasing our Q to, for example, Q to 0.9995, then the optimization is no longer converging because of this problem. And you can read more about these tutorials here about recurrent neural networks, and you understand more about how it works and some problems that may occur, especially in terms of these gradient problems, computation errors, where values are rounded to zero, or when we have exploding gradients. There are some approaches to solve this problem. One of these approaches is also called gated recurrent neural networks, also called GRU. And PyTorch also offers this class for gated recurrent networks. And we also have the long short-term memory networks, the LSTM. They are also very popular, in which they have learnable bypass connections or gates, which makes the computations of the gradient more precise. But for problems where simple RNN converges, it seems to converge faster also because the gated recurrent networks and the LSTMs, they have many more ways to be optimized. So here you also have this class for the long short-term memory, how it is implemented in PyTorch. But let's go back to our PyTorch model, and we will reinitialize the recurrent neural network now with random starting values. So we will not assign pre-calculated weights. We will give we will start or initialize the RNN with random values. Then it will be trained using 500 epochs. So this is the iterations for the optimization, and we will see if the network will learn this behavior as an IR filter. So now our target is our filtered signal that you are converting from NumPy to PyTorch. Remember, we calculated before our what was this filtered that is here. So this is from the results that we obtained using the IIR filtering with an impulse. Here we have our impulse, then we have our filter structures given by the equation here, where we have this A coefficients. We're calling K, going through it once more again, and this function will be the target now. And this is what we're doing here. Then we are now initializing our recurrent neural network weights with random values, and we can see here random values here. So now we don't have pre-calculated weights, but we have random weights. But now we also have target function. We use loss, mean squared error loss, and also we use an optimizer, which is the ADAM optimizer with default values. So what we want now is that our network learns this behavior, how to behave exactly like the infinite impulse response filter that we calculated before, by giving this target and running a complete experiment, and we will have then the output of our network. We will compare and we will see if it learned properly. So here, this is the standard way how we've been doing. So we have here, this is we feed this signal to our recurrent neural network model, we calculate losses, we use this zero grad, backward and step as usual, and after you'll see that the loss starts at 4.4 more or less, and after 500 epochs it's at around 0.1. It looks successful. So then we will plot the resulting impulse response from the recurrent neural network, and in comparison with the given target, which is the impulse response of the IIR filter. So this is the output of our recurrent neural networks. Here our model within this input signal. Input signal is an impulse, and then we will play it back. And it also sounds exactly the same as when we filtered using our IIR filter. When we assigned the calculated weights of our RNN behaved like an infinite impulse response, and also now we didn't assign any weights, but we gave it a target value, and it was trained so that it would optimize in order to behave like the infinite impulse response. And here is the plot that we are comparing. The in blue is the IR filter impulse response, also our target, and then the output of our RNN network. And we already see it looks very similar, and observe that now we have an even better fit than with our pre-computed weights. And this is because the training was able to partly compensate the effects of the nonlinear activation function we used, which was the 10H. And this approach can now be used to generate sounds and also to detect sounds. So for instance, this RNN could be used to generate the xylophone or bell sounds. So each impulse at its input is like an attack for a certain note of the xylophone or bell, and different targets in the training result in different sounds. Observe that this is now more generic than an IIR filter, and hence more sounds could be produced. Matched filter theory states that a filter is maximizing the signal to noise ratio for a signal which is the time reversed of its impulse response, and you can also see our lecture on convolutional neural networks. That is also available here. And since the RNNs, they have long impulse responses, they can also detect long signals or sequences. So this is the end of our tutorial on RNNs. There are much more to explore. There are much more to go deep into the gated recurrent networks, or the LSTM, or the other generative models like GANs. And this is just a basic introduction to machine learning for audio signals in Python. It's given by Professor Schuler for bachelor students, different courses, especially media technology, communications, and signal processing. And this is a prerequisite to go deeper, to participate in research projects in our group, and to start learning more about machine learning, deep learning for audio signals. So thank you very much for your time. I hope you enjoyed this series on machine learning for audio signals in Python. Please check our other tutorials. We have many more tutorials covering the subjects offered by Professor Schuler, subjects from our Applied Media Systems Research Group at the Ilmenau University of Technology. We have audio coding, we have multi-rate signal processing, we have advanced signal processing, and also I have other tutorials that are not related to the Ilmenau University of Technology, but they are related to sound and to audio programming, music technology. So we have the basics of musical instruments classification using machine learning. We have an introduction to automatic music transcription. We have the basics of embedded audio programming. So there are much more. So you can check the GitHub at Guitars AI YouTube channel. And I see you another time.